In these notes, we're going to talk about z-scores and the empirical rule. So first we're going to talk about the normal curve. So a normal distribution has a bell-shaped curve, and what that means is we take any graph, so for example the histogram that we have off to the right, and we can draw a density curve on top of that graph. And what that is, it's an estimate of the data. Okay, so this would be our density curve. Notice when I draw this, it is bell-shaped. Okay. What this density curve does is it describes the pattern of the distribution. What makes data normal? Normal distributions are appropriate for many distributions whose shape are unimodal and approximately symmetric. Now, talking about the normal distribution, we're going to give new variable names to mean and standard deviation. So before we were talking about sample, and now we are talking about population. So for a population mean, we identify that as mu, and for standard deviation, we identify that as sigma. And then altogether, we would describe the normal distribution as normal of mu and sigma. A normal distribution density curve has the following properties. It's symmetric around the mean, and also the center here doesn't really matter because all the centers, mean, median, and mode, are all going to be the same. We know that 50% of the observations are less than the mean, and 50% of the observations are greater than the mean, with the total distribution being 100%. Okay. Remember that standard deviation tells us how far things are from the mean, or how spread out. In a normal distribution, all data approximately lies within 3 standard deviations above and below the mean. So if we take a density curve like the one at the top, and we were to draw what that would look like in terms of the center and the standard deviations on either side, we would see that the center here would be mu. The first deviation would be mu minus sigma and mu plus sigma. The second standard deviation would be mu minus 2 sigma and mu plus 2 sigma. And then the third standard deviation would be mu minus 3 sigma and mu plus 3 sigma. Okay. So let's go ahead and look at an example. So in this example, it says the heights of American women age 18 to 24 years old with a mean of 65.6 inches and a standard deviation of 2.5 inches. Assuming the population is normally distributed, draw a normal curve and label 3 standard deviations on either side. So our population here is the heights of American women age 18 to 24 years old. Our mean is 65.6 inches, and our standard deviation is 2.5 inches. So I'm going to start with my mean, so 65.6, and now I'm going to add and subtract 2.5 on either side. So I get 63.1 and 68.1. Now I'm going to add or subtract 2 times the standard deviation, so that would be adding or subtracting 5. So 60.6 and 70.6. And then lastly, 3 standard deviations away would give me 58.1 and 73.1. Okay. Now let's talk about the empirical rule. In a normal distribution, we can describe variability or spread of the data in terms of probabilities. So notice here, we have a keyword, variability, and in parentheses, I put spread. So now we have several words that mean spread. We have the IQR, we have range, we have standard deviation, and now variability. Okay. So what the empirical rule states is that 68% of the data will lie within one standard deviation, 95% of the data will lie within two standard deviations, and 99.7% of the data will lie within three standard deviations. Okay. This is referred to as the 68, 95, 99.7 rule, or in other words, the empirical rule. These approximations can be used with the symmetry of a normal distribution to approximate proportions of data. So if I was to draw the empirical rule on this density curve, we would still see that the center line here is mu. And then on either side is one standard deviation adding and subtracting from the mean. So I'm just kind of copying down what we already did up there. Okay. Well, the first one says that 68% of the data is going to fall within the first standard deviation. Well, here's 68% of the data because this is the first standard deviation. So this is 68%. Then 95% is going to fall within two standard deviations. So this is 95%. And then 99.7% of all data is going to fall within the first three standard deviations. So this is 99.7. And of course, these are all percentages. Okay, so let's go ahead and look at some examples. Okay, so it says use the empirical rule. And our first example says the mean test score on the Unit 1 assessment was 82 with a standard deviation of 4. 95% of the test scores were between what two scores? So we know that 95% is two standard deviations. So I need to make sure that I find all the data in between these right here. So I know mu is in my center, so that's 82. The first standard deviation will add 4, which is 86, and subtract 4, which is 78. So right now that's 68% of the data. And then if I add 4 and subtract 4 again, so 74 and 90, now we are at 95% of the data. So that means 95% of the test scores were between a 74 and a 90. Okay, same thing on the next one. It says the mean age at the concert was 38 years old. Okay, the standard deviation was 5.5 years. Now it's asking what percent of the concert goers were between 32.5 years and 43.5 years old. Well, we first will do the standard deviation on either side. So if I add 5.5, I get 43.5, and if I subtract 5.5, I get 32.5. Well, notice how these values match up with the values that we're trying to find. So that tells us that since we only had to go one standard deviation away, that they are within 68% of the data. So 68% of the concert goers were between 32.5 and 43.5 years old. Okay. Now, what if we could get even more detail out of the empirical rule? And we would do that by calculating the small proportions between each standard deviation. Okay. In order to do that, we would first have to remember that two standard deviations away is 95%. Okay. And one standard deviation away is 68%. So if I wanted to find these values here, okay, that are in between the 95 and the 68%, I could simply subtract the values, so 95 minus 68, and that gives me 27. Divide by 2 because this is symmetric, and I get 13.5, which means that these values here is 13.5%. Okay, now what about the two center values here? Well, since we know this is the 68th percentile, okay, 68% of the data falls within that, I can divide 68 by 2, and I get that these are 34%. And again, I can do that because this is symmetric. Okay. Now, what about the two tails? Okay. So if I fill in everything I know so far, I know this is 13.5, this is 34, this is 34, and this is 13.5. I still need to find the two tail ends. Well, I know that the third standard deviation is 99.7%. Okay. I also know that the second standard deviation is 95%. So I could do 99.7 minus 95, and this would give me 4.7, and then divide it by 2 because it's symmetric, and I get 2.35%. So now in these areas, I know that this is 2.35. And then the only thing I'm left with is trying to find these very end tails. Well, if I know that the three standard deviations is 99.7, I can take let me rewrite that. I can take 100% of all data minus 99.7 and get 0.3, divide it in half since this is symmetric, and I get 0.15, which means the ends are 0.15% on either side. This is going to help us when we're trying to answer questions that want us to find the percentage below or above certain values. So in this example, we're still using the mean test score on Unit 1 assessment, which was 82, with a standard deviation of 4. So first I'm going to create my standard deviations on either side. Remember, we just did this one, so you're just kind of copying down what we already did. Okay. Then it says, what percent of the test scores fell below 74? So we want only this part right here. Well, we know that that broke apart into two percentages. That was 0.15% and 2.35%. So if I add these together, so 0.15 plus 2.35, I get 2.5%. So the test scores that were below 74 were about 2.5% of the data. Okay, the next one says, what percent of test scores fell above 78? So now I'm looking at all of this over here. Well, I could go and refer back up here, and I could end up adding up all these values. Or I could recall that I know half the data is on one side of the mean, which means this whole portion here is 50%. So I would only have to find this little portion here, which I know from the table above is 34%. So 34 plus 50 gives me 84%. So the test scores that were above a 78 was about 84% of all test takers. Okay. So using the empirical rule, we can do something even quicker, and we can standardize the data. Okay. So let's look at this example here. It says Mallory took a physics test and got an 86%. In the first scenario, the class mean was 97%. Did she do well? Well, we would say no, since relative to the class, her score was lower. So even though an 86 sounds pretty good, compared to the 97% class average, it's not that good. Okay, in the second scenario, however, the class mean is now 62%, which means yes, since relative to the class, her score was higher. Okay. So let's say, however, we are now trying to compare two things on a different scale. So two things that have a different scale. So on the first test, Mallory scored 86% and the class mean was 83% and the standard deviation was 4.5%. But on the second test, Mallory scored an 82% with the class mean of a 78% and standard deviation of 5.2%. So what we're going to do is we're going to actually calculate the z-score, or how many standard deviation away from the mean, to determine which score that Mallory got is better based on the different scales for the different scenarios. So for test 1, we're only using what I highlighted in pink. So we're going to take her score, which is 86, and subtract the class mean, which is 83, and divide it by the standard deviation, which is 4.5, and we get 0.67. If we do the same thing for the second test, we take her score, 82, minus the class mean, which is 78, all divided by standard deviation, which is 5.2, and we get 0.77. So if we were to interpret this, a z-score of 0.67 means that Mallory scored 0.67 standard deviations above the mean. And a z-score of 0.77 means that Mallory scored 0.77 standard deviations above the mean. And then remember, mean in this case is the class average. So the further above the mean, the better she did. So even though she got an 82 on her second test, she still did better compared to her class average versus the first test where she got an 86. Okay, so this brings us to z-scores. So it says if X is an observation from a distribution, and remember we're still talking about population here, we know that mean, or mu, and standard deviation, sigma, are values on this distribution, meaning they're known values, then we can find the z-score for X, where z is equal to X minus mu divided by sigma. So a z-score tells us how many standardizations we are from the mean and the direction, which means if we have larger observations, or observations that are larger than the mean, we know that we're going to have positive z-scores. If we have observations smaller than the mean, then we're going to have negative z-scores. So looking at an example here, it says female shoe sizes are approximately normally distributed with a mean of 8 and a standard deviation of 0.75. Find and interpret the z-score of a female with a size 6 shoe. So we know that this is normally distributed with a mean of 8 and a standard deviation of 0.75. So we have z is equal to 6 minus 8 over 0.75, which gives us negative 2.67. So in order to interpret that value, we would say a female with size 6 shoe is 2.67 standard deviations below the mean shoe size. Number 2 says Joe is 74 inches tall. The average height of an adult male is 70 inches tall with a standard deviation of 2.5 inches. Find and interpret the z-score. Well, same thing. We have z is equal to 74 minus 70 over 2.5. This gives us 1.6. So the interpretation would be that Joe is 1.6 standard deviations above the mean height of adult males. Notice in each of my problems, I mentioned the population. In problem 1, the population was a female with size 6 shoe. In problem 2, the population was the mean height of adult males. Okay, very important to include that context when we are doing our interpretation. So lastly, we have problem 3, and problem 3 is an AP style question, and here it's wanting us to compare two distributions. So Corbin's SAT scores with Corbin's ACT scores. So what I'm doing is I'm setting up two z-score formulas. So for SAT, I have z is equal to 1100 minus 1083 over 194, which gives us 0.088. And for his ACT scores, we have z is equal to 23 minus 21 over 1.62, which gives us 1.23. So since both of these z-scores are positive, we know that they're both above the mean, but since his ACT z-score is higher or more above the mean than his SAT scores, this tells us that he did better on ACT versus SAT. Not his score to start with, not his 23 versus his 1100, but his 23 compared to the mean of the test takers who took the same test of 21 versus the mean of the same test takers who took the SAT at 1083 means he did better. Okay, because I know there was some confusion over that in class. So we would say Corbin scored better on the ACT because he was more standard deviations above the mean.